the opportunity to be here and make this talk. And today I'm going to talk about our recent results on photoemission response from the fully electronic charge density rate ordered system in time-resolved quantum probe experiments. This work was done in collaboration with James Frerichs from Georgetown Univ and Rich Whitecop from Ukraine and Tom DeVroe from Stanford. The project was supported by the Department of Energy and computational resources were provided by NASA. James Frerichs did very nice introduction in the time-resolved spectrometry, so I'll just quickly remind the main principles. So, time-resolved quantum probe experiment is designed to learn about non-equilibrium state of the system, and it is a two-stage process. At the first stage, the high-intensity poles pump the system into non-equilibrium, and shortly after that, very short in time probe pulse provide electrons with the energy to let them go out the material and be detected on the screen. That's what you actually can see on this short movie. The pump pulse, the red pulse, pump the system into non-equilibrium, and then blue pulse let the electrons go out. In this slide, we present the experimental data for the time-resolved, angle-resolved photoemission spectroscopy results for the terbium tritelluride, which is charge density wave ordered material. And these figures show the time evolution of the response from the electrons in valence zone and with for different times of the probe pulse with respect to the pump pulse. So at early times there is a gap, which is charge density wave gap in the system. This horizontal line denotes the Fermi level, and at the moment of pump we see some response from the states above the Fermi level, and for longer times we see that the Fermi level is filled, so the gap is closing, it's collapsing. The same we see in this movie. Another example is the charge density wave ordered material, in which we have, in this case, the charge density wave ordered parameter is defined by the difference of energy between this and these two peaks, and this is in equilibrium. But during the pumping the system into non-equilibrium, this two peak structure disappears, and that's what we see for this delta energy between these two peaks. It decreases during the signal and then it recovers, but it never goes to zero. So on the example of these two experimental data, we see very interesting phenomena in non-equilibrium state of the charge density wave ordered material. On one hand, we see the fast charge density wave gap collapsing, and on the other hand, we see the collapse of the ordered parameter, but it never goes down to zero. So we are motivated by this to perform the calculation for the purely electronic system in charge density wave ordered state. To describe the charge density ordered state, one can either by involving two sublattices in a real space, or by nesting of the brilliant zone of the nesting vector in a momentum space. Modulation vector defines the sublattices in this way, and this picture schematically shows how we transform our lattice from uniform phase to ordered phase. And we work at Hell filling. Keeping that in mind, we can write down the Hamiltonian of the system, and we work with the pellicle-Kimball model, which is the simplest model that processes transition into charge density wave ordered state. They also describe the metal matte insulator superposition, and the main feature of this model is that it has the exact solution in dynamical mean field theory. So it has two terms. The local terms describe the on-site Coulomb interaction between I forgot to mention that it involves two kinds of particles: the heavy particles, which is local, and the mobile particles, which hop from side to side. So Hamiltonian has two terms. One term is the Coulomb interaction between mobile and localized electrons on one side, and the kinetic terms describe the hopping of itinerant electrons from side to side. Then we put this system into external electric field, and we involve the interaction with that field, external electric field, by viral substitution to the hopping matrix. And we have two order parameters in our system. One is the difference of the occupations between different sublattices of heavy electrons, and it remains fixed during the interaction with the external field. And another is the difference of occupation between different sublattices of light electrons, and it can change during the interaction because those electrons interact with the external electric field. Next, we are going to calculate the Green's function, which is a 2x2 matrix in this case, in case of two sublattices. And we exploit the dynamical mean field theory, which is known to hold in non-equilibrium as well. And because of our Hamiltonian depends on time explicitly, we had to exploit the Danov-Keldysh formalism. And it involves this time contour, and depending on which branch of this contour our times lie, we can define different Green's function, and so-called lesser Green's function defines the photoemission response. The theory for the time result, angular result, photoemission response function has been developed recently by Friedrichs, Krishnamurti, and Krushke, and it is the Fourier transform with respect to the difference of time of the lesser Green's function with the envelope of the probe pulse. And here sigma b defines the width of the probe, and we know that the bigger sigma b is, the better is energy resolution, and worse time resolution, and vice versa. K is the momentum, but in our work we present the results for the total response, so we sum over all k, all momentus, and T0 is the time delay of the probe pulse with respect to the pump pulse. Before we go to analyze our result for photoemission spectroscopy, photoemission response, we would like to mention about equilibrium phase diagram of the follicle-pinball model. So here we have the temperature interaction plane phase diagram. Here is a uniform phase. So this is the metal, this is molten insulator, and this is the charge density for the region. And here we distinguish three different regions. This region is the weakly correlated charge density insulator. This is strongly correlated charge density insulator, and this region we call correlated charge density metal, because here the density of states at the Fermi level stays non-equal to zero down to the zero temperature. So that's why we call it metal. Here we present the results for the density of states for in equilibrium for the case of weakly correlated charge density insulator. So we are on this line, and these different colors correspond to different temperatures. Inside here we show the order parameter for heavy and light electrons, and what we have at zero temperature we have the charge density gap, which is equal to U, and if we increase the temperature, this gap starts to fill with the subgap states, what we can see blue line and green line, and up to the critical temperature till we fill this gap with subgap states and undergo transition into uniform phase, which is the black curve. But we have to mention we had to notice that that this gap, it always still remains equal to U up all the way up to the critical temperature, which is different from the case which we have in DCS theory, where if we increase the temperature, the gap just shrinking. Next case we are going to analyze is the case we call quantum critical point. So we are on this line here. This scenario of temperature evolution is pretty the same, with that difference that all subgap states starts to arise at the Fermi level, at the chemical potential level here. And the last case is the critical mode insulator. So we are right here on this line, and in uniform phase we already have the mode insulator gap, which can be seen here, black line here. Scenario stays the same. Gap fills with the subgap states, but all the subgap states arise only within the curve for the density of states of uniform phase. Now let us analyze our results for the time resolved photoemission response function, and we start with the weakly correlated transistor insulator. We choose the poles at the Gaussian with a huge field which is equal to 30 here, and we found that for smaller fields we do not satisfy some rules. Otherwise we have to spend much more computing time to get good results. So here there is response with respect to different times of the probe with respect to pump hole, and different planes correspond to different temperatures, and we keep the same polar schemes as we showed for the density of states. And we see for the case of the lowest temperature that before the pump there was the Chern density gap here. There was no response from the states on the Fermi level. Then during the pump, part of the electrons from lower band get excited to the upper band, and we also see the shrinking of the band during the probe pulse. And after the pulse is gone, we see the relaxation. And in this figure, we show more clearly that case of lowest temperature. So once again, before the pump, there is only response from the lower band, and during the pump pulse, there is excitation into upper band, and it remains till the long times. And we also see that gap is closing, and the same is seen in this movie. Here we present the results for the order parameter. So before the pump, it was almost flat, then it get excited, there was some oscillation, and then it recovers for some non-zero value. Here we present the results for the integral over the energy of photoemission response function, which should be the same for all times, but we get that for the extreme times it deviates this rule, so we here include only the results for the times from this black circles. Next is the case of quantum critical point, and this case differs from the previous case because we see that during the pump, only the very small fraction of the electrons from the lower band get excited to upper band, and they get de-excited right after the signal is gone. More clearly, it's seen it's here. So once again, only a response from the lower band electrons, then excitation into upper band, but very, very weak, and then de-excitation to lower band. So we find that this is very specific channel of the de-excitation, and we suppose that the excitation process and de-excitation process are in equilibrium in this, for this case. And the same is for the order parameter. It gets excited, get oscillating, but after the pump is done, it recovers for this, almost the same value. And finally, we get the result for critical mode insulator, and in this case, we also get very big part of electrons get excited to the upper band, and it persists for longer times, which remind us to a level atomic system when one needs to get another energy to the system to get electrons from this upper level get de-excited to the lower band. So this is basically all what we would like to present today. And in conclusion, we present an exact result for time resolved for the emission response in a short-density ordered phase for the volatile Kimball model. We examined 3 phases with different Coulomb interactions, and we found that including manic-body correlation into the short-density wave greatly enhanced the relaxation and the excitation processes. Thank you for your attention, and if you have any question, you're welcome. Open for questions. Yes, Rick.
Sorry about the finish counting the experimental results of the
Because with the previously we made the calculation in that direction, but for kind of another system, and we also see the gap closing, and these results, experimental results, that just amazed us that we can see something experimentally similar to our theory. So that was an indication.
Do you also have any comments or suggestions as to what the experimentals should report with under your
Not yet. Yes.
Many of these systems, like say chromium, where you have spin waves and turn waves, they're different probes are accessing different ones to what they're sensitive to, the whole present. Is there something in your theory that could distinguish between one and the other? I guess what I'm asking is part of this that be from the spin wave, or is it just applicable or not applicable? Curious about how it goes in.
In our model, we do not include any spins.
Okay.
So we
Would it
describe
break
only.
down in that case?
Excuse me.
Would it break down in that case, or is that something that would be extended to?
I don't know. We just need to write down the Hamiltonian with the spins and try to find out what the emission response function. Then we will get some results. So I don't know.
That's easy, man. Well, thanks.
Any more questions? All right, if there are no more questions, let's thank the speaker. We have